Hello and welcome to the presentation of the paper Learned Optical Flow for Intra-Operative Tracking of the Retinal Fundus. My name is Ravasio. I am a PhD student at University College London and a research assistant at King's College London. My supervisors are Linda Cruz from Moorfields Eye Hospital and Christos Bergeles from King's College London, who is the leader of the Robotics and Vision in Medicine group. First, we'll start off with some background. Vitreoretinal surgery is minimally invasive or keyhole surgery inside the eye. Incisions are made into the sclera, the white of the eye, to the side of the lens, in which so-called trocars are placed, through which the tools are then inserted into the eye. And the surgeon can see the tools through a microscope that looks through the eye's lens towards the back of the eye, towards the retina. Some of the tools that are being used can be seen on the right-hand side: forceps, cutter, light pipe, and there are others as well. Now, new procedures are being developed that aim to deliver, for example, genes or stem cells to specific retinal locations. This requires a higher precision than what the surgeons can currently deliver, because all of the vitreoretinal surgeries are purely manual. And there is just a physical limit to the achievable precision. So novel robotic tools are being developed to address this. And for these robotic tools, it's necessary to have computer vision-based knowledge of the retinal motions, for example, to track surgical targets. The problem is that this is very challenging due to the quality of the intraoperative images that we get. These are recorded through the microscope by a camera. So here we see two clips from our internal database called RIDE. RIDE comprises intraoperative retinal image and video data from 66 patients, and these were acquired during a variety of vitreoretinal surgeries, all at Moorfields Eye Hospital. We can see different types of motions, we can see the tools there. To the left-hand side is the aforementioned light pipe, which illuminates the scene. And we can also see how that casts a shadow, tool then casts a shadow. We can see the retinas are not always uniformly colored. So there is a number of phenomena that make the tracking of points on the retina very challenging. Here are a few of them put on one slide. So for example, the shadows cast on the retina. The tool is sometimes not easily distinguished from the retina. You can have glare on tools and also sometimes on the retina as well. There is blurriness, shape distortion. The field of view from the microscope is not always perfectly round, but can be partially occluded as well. The lighting itself can be uneven, sometimes dim, sometimes a little bit too bright as well. And in other cases, the lens is partially visible and there might be particles or droplets on the lens. So these white hazy spots that are visible there are actually on the lens and will move independently of the retina, obscuring part of it. And finally, the camera that records this video data produces compression artifacts, such as the ones visible in the last image. So what is our approach to deal with this? We decided on using optical flow for dense motion estimation. So we get one motion vector per pixel in the image to maximize our knowledge of the retinal motion. We estimate this optical flow using deep learning for better quality and fast inference. This is based on FlowNet by Dosovitsky et al., but we also have a combined segmentation output as a secondary task. Then we use, for domain and task-specific training, we use synthetic data. We want the algorithm in the end to be able to ignore occlusions such as tools and shadows and other effects like reflections and glare. And we want it to be able to predict the retinal motion even underneath such occlusions. So when the retina at one spot is actually not visible, which means the optical flow in that case has to be implicitly inpainted from knowledge of the motion of surrounding visible retinal areas. And we validate this on real intraoperative benchmark video clips. So to put this in one schematic, this is an overview of our methods. So we have the intraoperative dataset right and top middle. This has surgery videos and walkthrough videos. Walkthrough videos are taken just before surgery starts, and they just show a wider range of the retinal fundus with fewer unwanted effects such as tools and shadows and all of those, meaning that the images from the walkthrough videos can be used as a kind of raw material to build our synthetic data. We'll get into details of how the synthetic data algorithm works just after this, but for now, the important thing is that the output of the algorithm, meaning each record in the synthetic dataset, consists of an image pair, frame 1, frame 2, the corresponding segmentation pair, segmentation 1, segmentation 2, and an optical flow ground truth that will warp frame 1 to frame 2. So this purely synthetic data is used to train the neural network, the classic encoder-decoder structure, which is then tested purely on real intraoperative surgical videos from our testing benchmark series that are taken directly from the surgery videos. So let's look at the synthetic data algorithm in some more detail. The user defines the desired transformations, translation, rotation, lens distortion in this case, and a light cone as a non-motion transformation. And for each of those transformations, the actual transformation parameters are randomly sampled from a uniform distribution with limits that are also given by the user. So for the translation, for example, the maximum amount of translation, or for the rotation, the maximum amount of rotation. Each of the motion transformations then leads to one flow field, which is visualized here in the usual way, hue being the direction of each motion vector and the saturation corresponding to the magnitude of each motion vector. These three flow fields are then added up. Rather than just adding it up at each pixel, we do this mathematically correctly for sequentially applied flow fields using a flow field toolbox that we wrote ourselves. And this leads to a total flow field seen to the right. Now, the retinal image that is being used is randomly selected from a pool that is also given by the user. And we then apply this combined flow field to that retinal image, which leads to the image at the bottom middle. And then we apply all other non-motion transforms on top of that. So for example, the light cone, which leads to the final image to the right. However, all of this only leads us to one frame, one image. So this needs to be repeated for frame 2. And because the parameter of the transforms are sampled randomly from the distribution, frame 2 will look different. And the overall motion field that is calculated will also look different. However, we actually need the ground truth flow between frame 1 and frame 2. So this is calculated from those two total flow fields, again using our flow field toolbox. So this is the ground truth flow that will warp frame 1 to frame 2 correctly. However, all of this is just one layer. So we see the synthetic data as layered, where the retina here is layer 1. And for this example, layer 2 is the field of view. We could, however, also have more layers. For example, the light pipe could be one layer, and an instrument or tool coming in could be another layer. For each of these layers, we extract masks from the alpha channel of the images, and then mask the images and the flow fields and construct a partial segmentation as seen on the right, which can then be combined and essentially merged down into the final images, frame 1, frame 2, the final segmentation, segmentation 1, segmentation 2, and the final flow field to the right-hand side. Now, the transforms that are implemented should replicate the phenomena visible in intraoperative images, the ones mentioned before. And so in the following, we'll see how those previously listed effects are simulated for example, the shadows cast on the retina. To the left, the image we've seen before from real vitreoretinal surgery scene, and to the right, some synthetic data simulating this. The same for a tool that isn't entirely distinguishable from the retinal background. Glare on tool shafts, or blurriness, shape distortion, partially occluded fields of view, uneven or dim lighting, here with the light cone effect that was mentioned in the example before. We also have the case where the lens is partially visible and we might have particles or droplets on it. So in this case, in the right-hand side picture, the dark smudge is actually simulates a drop that is on the lens, and it'll move independently from the retina underneath. And finally, we also simulate the compression artifacts in our synthetic data. This effect is added at the very end when the image is otherwise complete. So in a typical record in a dataset, with only showing one frame here, but frame 1, let's say, segmentation 1, and the flow field corresponding to it, these effects, so light glare, shadow, a light cone, and those moving spots on the lens, all of those are not visible in the segmentation because they are not actual objects that we're interested in. And they're also not visible in the flow field. So the flow field ignores all of those effects. Now, specifically for the task in this paper, where we want to robustly track points on the retina, even when the tools such as the light pipe or the instrument are obscuring that point, we actually suppress the segmentation and the optical flow output for the light pipe and the instrument, leading to the segmentation and optical flow ground truth seen on the right. So when the network is trained with this data, it'll learn to observe the tools, but fill in optical flow for those pixels from surrounding context. The neural network architecture that we use is, as mentioned, based on FlowNet. So it essentially is a fully convolutional unit with skip connections. However, we have two tasks. So we have, on the one hand, we want a flow field, optical flow prediction as one output, and then as a secondary output, we want a segmentation. We explored two different ways of combining those two tasks in one network, one of which is visible on this slide, where they share an encoder, but they have separate decoders, with the flow being predicted at different resolution levels. And the second architecture that we tested combines the flow and segmentation output in one at every resolution step. So they are sharing both the encoder and the decoder. Now, to get to the results, as a baseline comparison, we looked at two variational methods that are visible on this slide. So this actually illustrates the problems with just naively tracking points on a grid. Here you can see how any point on the retina, when a tool or even a shadow passes over it, is gathered up and moved with the tool. In addition to that, you can also see how very strong features dominate the tracking process. So you can see how glare as a strong feature is, each glare patch is tracked individually, even when the glare patch, for example, is moving up and down the tool shaft. And to avoid this, all of this, in contrast, we have our method here, where you have tools, shadows, glare, moving over points on a grid, and yet those points are still being tracked with the retina and coherently as a grid with each other. And you can also see the flow field on the right-hand side that looks, in comparison to the variational methods, clean, and you can see that the tools are not visible in there. And here's a second example as well, again with shadows, tools moving, lighting variations, glare, all of which has no direct effect on any pixels retina that are being tracked. So we did an extensive evaluation of this. For details, see the paper. The main evaluation benchmark series, that's 32 sequences of 200 frames each, all taken from the surgical videos in the right dataset. And we see significant performance improvement compared to the two different variational baseline methods. And so we evaluated a number of different network variants with and without the segmentation combined in, and with the two different architectures shown before. We did a network width ablation study, dataset size ablation study, and we tested datasets of different complexity. Unsurprisingly, using a less wide network or using less data to train it reduces the performance. Similarly, using a less complex dataset also reduces performance, and maybe more important to mention, it reduces performance quite significantly, which suggests that the work done to simulate the real data convincingly is indeed relevant to the performance that we achieved. So our conclusions: we have developed a flexible, layered algorithm to create large synthetic datasets of intraoperative image pairs, segmentation pairs, and optical flow ground truth. We have shown that optical flow learned from correctly designed domain-specific synthetic data can be used to robustly track points of interest on the retina, even in the presence of occlusions, shadows, and the like. The complexity of the synthetic data that is used is important, and it increases the achievable tracking performance when it's more complex and simulates the real data more convincingly. And finally, the convolutional neural network used does benefit from simultaneously predicting a segmentation and an optical flow prediction, which supports an initial assumption that we had that those two should be mutually beneficial tasks, because wherever you have an object border, you tend to have motion discontinuity and vice versa. I'd like to finish the presentation with an outlook. So we are currently working on extending this algorithm to a scene understanding of vitreoretinal surgical videos, where we essentially decompose each frame into the same layers that we compose the synthetic data with. So we want to be able to segment and track the retina individually and each tool individually as well. This is on the one hand necessary for the control of those robotic tools that I mentioned in the introduction, and another more direct application for current surgeons that we are developing with Linton Cruz from Moorfields Eye Hospital is visible in this mock-up here. So this shows an augmented view of the retinal fundus. Here, in the dark patch underneath, we now see more vessels. This is OCTA, a different image modality that is here being registered to the fundus and then tracked with it. And this could either be tracked with the white cross, which represents a surgical point of interest, or it could be tracked with the tip of a tool. In this case, in this mock-up, I'm moving the tool with the cursor, but obviously in the actual operation, the surgeon would be moving the tool, and then the algorithm would recognize the tool tip and augment the image at that location, giving the surgeon more information about what is happening underneath the retina at that point. Thank you very much for your attention.